So the goals for today's talk is you understand what are Earth observation foundation models. We talked about them a little bit, but nobody's really kind of defined what they are, so I thought I'd give that. And I want you to see one in action. I want you to see at least one way to evaluate them or to start to look at them, some of the terminology that's used, and hopefully everybody except Jimmy has a really good time. So let's just say what is a foundation model? Right, so what are they? A foundation model is a large AI model trained on broad data that can then be adapted for a wide variety of downstream tasks. Right, so there we have you hear these outside of the geospatial space, but we actually have them as well. It's usually pre-trained on vast amounts of unlabeled data. Right, so it's usually labeling unlabeled. That's not actually true. It's just usually trained on vast amounts of data. Uh, More than an individual or one little organization is going to grab. Usually they can do transfer learning. The ones we care about today are open weights. You can do things like RAG and other things which are considered uses of like the OpenAI models for as a foundation, but the ones we care about today are ones that are actually using open weights where we can actually run our own machine learning code with them and improve them for our use case. To build them, they're generally very expensive and time consuming to build. These are usually built only by the largest organizations or by Bruno because he likes taking on that challenge. And then some examples of foundation models are Llama, like the whole Llama series, like Llama 3, right? That's a foundation model. OpenClip, that's a computer vision foundation model. Janus, which just came out from DeepSeek, right? That's a multimodal, kind of like OpenClip, but I think it's geared a little bit more towards text, but it does do multimodal text and images. AudioCraft for this, you can use this for fine-tuning audio machine learning. StarCoder, this is another model put out for fine-tuning that you can fine-tune for coding tasks. So these are all examples of different kinds of foundational models, right? But do we have them for Earth observation? And as you saw in that scrolling list before, yeah, we do quite a bit. I was shocked at how many we have. There are actually quite a few. So these links from the deck, if you get the deck and these links go to that scrolling video you saw for the different categories. So we have the vision foundation models, right? So that's just the straight up ones like Clay and the other ones. But we also have ones that are like vision language foundation models. So this allows you to actually use language to query for remote sensed images or things in remote sensed images. We have remote sensing generative foundation models where you can actually generate scenery or generate models based on remote sense data. We have vision location foundation models, right? So that you give a location or you give an image and it tells you the location and vice versa, right? We have vision audio foundation models. There's remote sensing task specific foundation models. I'll let you look at the link to see those. And there's actually even a section on remote sensing agents, which is the hot new buzzword. These are usually the way I think about this is pieces of software that coordinate and call different models depending on what the task is at hand. We also, for us in the geospatial community, this community has a long, strong foundation tradition for using open data and making things open, as you saw with Clay and also with Mikkel's stuff, right? And source.coop or source.coop or whatever you want to call it. There's benchmarking data, right? That's out there. There's benchmarks. There's a freely shared large scale pre-training data sets. And also Hugging Face has a bunch of data sets as well. So if you are in the machine learning computer vision space and you want to just get your data straight from Hugging Face, they're there as well as some of the models. All right, so there is plenty for you to work on here, and it's like most of the models there are from 2024 onward. So this is an active area, and that I hope that person, whoever's maintaining that awesome list on GitHub, keeps it up to date because there's a lot of research going on, papers coming out all the time. So that's kind of the basics of foundation models, and for those of us in the geospace where you can go find more, I actually want to now, since we only have a half hour, switch to getting to work, right? So let's show some stuff. The question that we're going to try to answer, because I think just like Mikkel said, so what are we using this for? What's the purpose? All of these things, they should have a question behind them or some sort of use case that's driving them. And so the question, because I live here, is how well can we train the Clay Foundation model to recognize land use, land cover, particular to the Santa Cruz, California, USA region? And I'm going to do semantic segmentation. And so for those of us in the remote sensing community from long ago, Semantic segmentation is another way for saying I'm going to create a land use land cover map, right? I'm going to take every pixel and assign it to some category. We used to do that all the time. I mean, I think that's one of the things of starting in the remote sensing community, having done this kind of work way back when, and then coming kind of fresh to computer vision. What I've enjoyed is, oh, I don't have to do all those edge detection algorithms anymore, or all that other stuff that I used to do. The model actually will do that better than I can underneath the hoods. And so I thought it would be fun to I've done semantic segmentation manually in my former life, and it would be great to try to see how it works now in the new and improved life. So one unspoken secret I want to lay out here for everybody right from the beginning, though, when you're looking at fine tuning or talking about fine tuning, to be able to do this work, you need to understand. So here's some things you need to understand, particular to remote sensing or Earth observation, whatever you want to call it. You need to understand remote sensing and Earth observation, right? The field is different than some of the straight up normal computer vision, like recognizing numbers, handwritten numbers, and things like that. There's different things to think about. You need to understand image processing some because you will be doing it to preset, get your data ready. You need to understand Python. Everything that I've seen has been doing this in the Python world. And you do need to understand computer vision, right? So like you do need to understand how computer vision models work and some of the processes involved. I highly recommend getting comfortable with PyTorch. These are all things that are kind of crucial. And this is the one that I think uh, people really need to let sink in a little bit. The knowledge and skills required, while not quite as great as building a foundation model, are not trivial. So I love Bruno's aspirational goal, and I love what Mikkel's doing to make it more widely accessible. But if you're going to get into fine tuning at this point in the game, especially in the geospatial world, we don't. You need to know a lot, and you need to actually know some of the details. You don't necessarily have to put together all the like all the layers in the neural network and all that stuff, but you have to kind of understand what a neural network is doing and what's happening during different phases in the code, right? So less intensive than making a foundation model, not as easy though as just using an app like what like what Earth Genome is making, right? Um, so I just want people going into it with eyes wide open. It's doable. It's not where Bruno wants it to be right now. And they've done a lot of work, which makes it way easier than it would have been, just like Mikkel pointed out. Like it had Clay been around when they started their thing, their project, or Prithvi or any of those others, they probably would have chosen one of those because it would have saved them a lot of time and money. Okay, so but the key point is like if you've worked with like Llama 3 or ResNet or YOLO V8, right? Those are all very popular models with a lot of infrastructure around them to make fine-tuning a lot easier. They have a lot of sample codes. Well, first of all, Llama 3 is easier just because it's NLP and not remote sensing. But for these others, like this is going to take a bit more digging in at this point in time for the evolution of our community. Hopefully in the next year or two, we'll see things get a little bit more standardized, just like Bruno pointed out. But right now, this is not you got to be ready to take on a bit more. All right, with that, uh, these are the things that you kind of have to understand that makes it different from those places, especially NLP, right? We're dealing with concepts of space, so you have to like we're doing spatial things, which don't happen in NLP and those other places. There's time, even if you're not accounting for it in your model, you actually have to think about it as you're thinking about your data and what you're doing. And you'll see that with my terrible results I got from fine tuning, why it's important. There's usually more than three bands of information, right? Like MNIST, I forget how it goes. They started with grayscale, right? Most remote, like the car camera pictures, they're all three band, right? Red, green, blue. For most remote sensing, especially the ones that we've seen today, they're all not hyperspectral, they're multispectral, 6 bands, 8 bands, somewhere around there, like Sentinel and stuff. The future is hyperspectral. So there's a lot more than 3 bands. And so the way you work with that image and the stacks and all that stuff is different. How you display them is a whole different thing. We'll see that in a second. And these are usually large images, right? We're not talking about the original image being like 1,000 by 4,000 or something like that, right? They're usually really quite large in size. And so that causes us to have to do different things than you would usually expect from a normal, like, here's the picture, find my friend in it, right? That kind of stuff. So what we need to do our question is imagery data. So I used harmonized Landsat Sentinel data. Uh, I think that's what HLS stands for. This is a good use of my tax dollars. NASA and some other groups, I think the Europeans as well, the Sentinel data and the Landsat data are close enough in bandwidth that they've actually started to work now on creating a harmonized data set which combines all of them together across all the bands available across the entire time series. So this is the data we're going to pull today. That link actually brings you to their homepage, and that's the data we're going to be using. It made it very easy for me to get satellite data compared to how it used to be. Ground truth. So since we're doing segmentation, I don't want to go through and hand draw pixels on there, hand draw polygons on there and then turn them into raster images. I found a land use land cover from the Conservation Land Networks for the Bay Area, and we're going to use that as our truth, or as our ground truth, right? So we're going to say overlay those on top of each other and say whatever that raster image from the Conservation Land Networks is, that land use land cover, that is the true land use land cover that we want to train towards. This is, Bruno talked about this a little bit. This is what you have to do for any of these segmentation or any kind of thing. This is pre-labeling. And then code from various locations. So those are links to the GitHub repos, one for pre-processing and setting up the data, and the other for how I actually ran the fine-tuning. They're blatant copies, and then a bunch of other stuff that I did on top from other amazing people who've done really great work. Right? So we need data and we need code and the GPU in my laptop. The data information. So this is a problem. The land use land cover is 110 land use classes, and I'll show you why that's a problem later. Not all of them are present in our study area, though, the area I cared about. The land use land cover was originally 5 by 5. I had to upscale on the line to match the imagery. It was presented as a one-band integer geotiff. I'm giving you these details. I'm going to go quick, just in case you're thinking about this and come back to it later if you want to do the same stuff. 6 bands of spectral information. I did blue, green, red, near infrared, shortwave 1 and shortwave 2. This comes back from HLS as 1 geotiff per band, right? And then this is at a 30 meter by 30 meter cell size. So we upscaled the land use land cover to 30 meter by 30 meter cell size. And I started collecting satellite imagery on March 16th, my birthday last year. And I ended it right around Thanksgiving on last year. So we're taking any satellite images in our area from that time period that meet a certain level of quality. I was basically trying not to get the rainy season here, but we still had the fog season. So this is what the study area looks like, right? The colors, that crazy colors, that's all the land use land cover classes, 110 of them. The black lines are the road network, just to kind of situate you. The star is the center of the universe, the best place in the world, right about my house. And that purple with all the lines on it is Santa Cruz. Up here, that's San Jose, and San Francisco is somewhere way up here. And that scale bar is just to give you an estimate of size. That's the area where I cut out as my study area that I was interested in. Okay, so let's look at some of the initial images that came out of HLS. So here are the initial images out of HLS I'm looking at them in 51 right now, right? As you can see, this is the red, green, blue. This is just a normal imagery color bands I've chosen to do here. Let me show you some interesting things. Like you see this. So you want to see that in red, green, blue? Or should we look at that actually in false color infrared? Let's do false color. Actually, you know what? I haven't done it much. Let's do SWIR. So this is using shortwave. Green is like the darker the green, the more vegetation and the more moisture. And then purple's are urban. This is the beach right here. So this is sand, right? So one of the things you'll notice right away here is these holes. These holes are cloud cover, right? So I did not correct for this. So this is a rough and dirty, quick and let's just do this thing. I did not correct for this. There's also a band that comes from HLS called FMask, which gives you information about each pixel, about how good the quality is and all this stuff. You'll see how this comes back to bite us later. You might ask also, we were talking about getting imagery together. Notice that for some of these, the chunk is very small. That's because the overlap of the satellite strip with my study area is actually quite small. This one's got clouds over most of it. This is probably clouds up in the mountains or it's actually probably fog. But some of them are clear with a lot of the pixels in. But that's the general data. And if we wanted to, we could actually also look at this in all of these in the different colors if we wanted to. All right. So that I like having this overview like this and quickly being able to get a sense of all my imagery without having to keep changing Jupyter Notebook, right? And I can scroll through and then I can dig in if I want. All right, so that's our full images. These are the images we're starting from. You already saw the land use land cover in that graphic I did. Let's go back to our slides. So what I did with this is I have to actually chip this, right? Because our images are so big, we actually have to take that larger, for each one of those images we saw there, we actually go ahead and chip them. Chip them means to cut out small little cookie cutters of them, of both the imagery and the land use land cover, so that they make sure those two overlap, and that becomes one chip, so that it's an actual size that current neural networks can work with. Clay is arbitrary about its chip size. You can pick whatever size you want, but most of the training was pretty close to 224 by 224 pixels. And a lot of other models like Ph.D. Also use about that size, so I stuck with what seemed to be a standard size. That gave me 7,584 chips over that entire study area. So that is the number of chips I could take over all those images, given the extent of the study area. And I took out 2,500 for training, just in the interest of time. I didn't use the whole data set. I used 500 for validation. So that's during the fine-tuning stage. The model trains, and then it validates that training using those 500. And then I took out 500 for testing. So that's after I fine-tune and then predict on these new areas to see how we did. I ran this for about 100 epochs. So I took the Clay model, the fine-tuning. They have a really nice example on segmenting the Chesapeake Bay. It's using NAPE data, National Aero. It's basically aerial photography for the whole country. They actually produce, like Mikkel talked about, cloud-free images for a certain area by putting a whole bunch of stuff together, by putting a whole bunch of images together to create a mosaic. Anyway, this is what my training looked like. If you'll notice, IOU is intersection over union. And basically what this says is how much do the predicted pixels align with the ground truth pixels, right? So a value of 1 means there's perfect alignment. A value of 0 means there's no alignment between the pixels, right? And so usually a good model is about 0.6 to 0.7. You can see after 100 epochs, I'm basically leveling out at 0.14. So the same thing kind of happens with the F1 score. This is basically a balance between precision and recall. Precision being like, how much is that pixel? How much do I believe that pixel really is what that pixel is? Recall is how many pixels did I miss that were actually the type that I was looking for, right? And so this is trying to find a balance between the two, and we seem to be leveling out at 100. That's about as good, and we're only at 0.16. Same thing, 0's terrible, 1 is great. So let's look at the results. So I go back here into 51 and I pick out the clay data, right? So these are our results. Right now, we're just showing the dark green is the ground truth image on top, and the blue underneath is the predictions. So you see only some of them have the predictions, which is what I said before. So what we can do though, you're like, that's not very helpful to just see these blues and greens. What should I do? Well, so what I can do with this is I can actually change. This is now just showing it all as one. What I actually want to do with this is, sorry, color palette, and I want to go down to the ground truth, and I say color by value, and I'll say the same thing with prediction, and it already changed it to color by value, and I'll just what's that? And so now we can see the predictions on top of our images, and we can change the images underneath. So let's actually just open this one to start with. Again, this is TIFF. Let's look at it with the SVEG underneath again. Well, now those colors are kind of actually. So if we turn off ground truth and prediction, here's what we're looking at, right? Oh, this one doesn't actually have predictions. So we shouldn't do this one. Let's actually look at one with predictions. All right, so I want to look at one that has predictions. Let's see. So predictions, I'll open that up. I'll get one that has a particular one. That's a pretty good one, right? So there's our predictions for that image. And we also have our ground truth turned on right now. It's kind of hard to see with that green, but let's go ahead and look closely. So what we can do here is I'll turn them both off. We can get an idea of where we're looking at. It looks like we're in the mountains somewhere with a lot of clear and a lot of forest. So if we look at the ground truth and we mouse over, we can see these are warm grasslands. This is coastal mixed hardwood. This is coast live oak, right? And if I then turn on the predictions on top, you can see well, before I look at the labels, actually, if we do this, right? So we keep predictions on, we turn ground truth on, there's ground truth. We look at predictions, you can see that the shapes, it's starting to get pretty good shapes. It's capturing the features. You can see the model actually like picking up on the features in the image. But the problem that we're really getting into with the model and why it did so terrible is it classified this as all non-native invasive forb, and this is all flooded row crop agriculture, right? So it's getting the shapes right, it's getting the areas, it's doing a good job of segmenting out the areas, but it's doing a poor job of actually figuring out what the class is, the appropriate class is for what's happening there. And you're like, okay, great, Steve. So that's nice and visual that way, but is there a more systemic way that I can actually look at this? So let's go ahead and bring back all our images again. And in 51, we have the ability to look at models. So I did an evaluation of my test set, right? The prediction set that I did. And you can see our accuracy and precision are terrible. Basically, the shapes are great. I wouldn't do anything really with the labels. And I'll talk about that just one quick second. But I think the most important one that I like looking at here is the confusion matrix, right? And that's too many. We have too many classes. So I'll just change it to 25 classes, save, and then there we go. So you can see, like, so here's ultramatic. Let's see which one. Oh, actually, I didn't do it the way I wanted to do it. And I want to sort by the most common classes, and I want to use the logarithmic scale. Save. Okay, so for example, coastal mixed redwood, it got 32,669 pixels correct, where coastal mixed hardwood matches the prediction of coastal mixed hardwood. So if I do this and I split the screen and I go back to my confusion matrix, it reset it, unfortunately, but let's go back and go to 25 classes. Let's change it to most common classes. Let's use save, right? And so we were looking at coastal mixed hardwood. Oh, I actually did it. I don't think it saved oh yeah, it didn't save. There we go. Coastal mixed hardwood was right like here. Yeah. So if I click on that, it actually made us query up here. These are all the images where we at least got some of the coastal mixed hardwoods correct, right? There are some pixels somewhere in there where coastal mixed hardwood is predicted as coastal mixed hardwood, right? And if you wanted to, you could say there's count 0 of all these other ones, right? But if you wanted to see where is it doing poorly, where did it predict Doug fir, but it was actually eucalyptus, you can click on this, and these are the images where that occurred. One of the other things I like about having this big visual overview is we can quickly start to see that something's wrong with the data because it's making predictions out in the middle of blank spaces. So if I go to this image, right, and I turn off ground truth and prediction, that's why it actually was kept in, whatever that is down there, because I did really rough and ready data. But it should have known however I set up the model, I did something wrong because there's no ground truth data there, but for some reason it predicted across the whole thing. And there's multiple reasons why this could happen, but this is a good sign that something's wrong with how we set up the model, which would be hard to do if I had to keep going through each one individually. Okay, so I just wanted to show you what the outcome was. Let's go back and wrap this up. I might go through this a little quick because we're almost out of time. So specific problems, way too many classes. This is really unfair. Like asking, especially with only that many samples, but 110 classes is a lot of classes, right? I think in the future, I'm probably going to rerun this when I'm going to group classes to classes of interest for me. Pick a question that's either dependent on LULC, right? So I could do things such as fire risk or the Steve index, like places I really like for whatever various reasons, actually, and make that into my ground truth and then try to predict that. 110 is too much. So I think Clay, I don't remember exactly. I think it's like 15 classes it was trained on, maybe 20 as the foundation model. I think it's fine to fine tune to another 15 or 20 that are more specific to me, but 110 is just way too much. It's just too much. Annotation differences, right? So this is the annotations. Our land use land cover was not actually done on the actual image. The land use land cover was created as an quote unquote average. It's like whatever the GIS analyst was doing to create that land use data set, which is probably an amalgamation of several different data sets, and it's amalgamations over times both time of day and the actual day of the year, right? So it's probably not a totally accurate, especially its time. It was, I think it was produced in 2020, and we're looking at images in 2024. There's changes as well. Right. It's based on multiple sources. Right. Another problem was alignment and data consistency when chipping, multispectral and land use land cover. This comes into stuff like, I don't know how many of you, well, in the GIS world, we used to say yeah, it's great about maps, but you're going to actually probably spend 75 to 85% of your time actually just working with data. And that same thing, it's the same thing as statistics, and it's the same thing here. There's no getting away from that, right? The most important part was the data and the processing, and there was some trickiness about clipping the clipping the land use land cover by the chip boundary. Sometimes it was giving because anyway, long story short, raster IO clipping, you need to know some things that I would go back and redo. A chip of data is not a full chip. So in some cases, a chip of data can be full data, right? Like it was completely covered by a satellite image. But in some, it was not. So you run into boundary issues, both where it's the ocean and you don't want anything there, but it could actually be a boundary difference between the land use land cover and the imagery. And then as I showed you, all those holes for cloud and fog. Again, like everybody else has talked about, I think multimodal is probably going to be one of the ways to get around this in an area like Santa Cruz, where there's a lot of fog and grayness in the winter. Uh, Multimodal LiDAR and SAR could probably help with this as well. Right. And then I should have taken longer time sequences and tried to create a single complete image that was like a monthly compilation. Like say, this is the December image. This is exactly what Mikkel was talking about them having to do. And I probably should have done that as well. Having each individual day with all those holes in it actually probably added more noise to the model than this is a case where it would have been better to have higher quality one image than multiple lots of images with lots of gaps in them, because I think that was way too confusing for the data. So, summary. Foundation models are an amazing gift. They are truly a gift, right? Like no one had to do this. Bruno didn't have to put all that energy and effort in to make this model and make it relatively easy for me to fine train and do what I want with it and do it for whatever I want to use it for. So they're flexible for many use cases, right? The future is fine-tuned. I really believe the future for most things is there's going to be like a suite of foundational models, and then people are picking those based on their characteristics and then fine-tuning particular to their use case, probably actually even making them smaller. Who was it that was, oh, there was a question about real time in Bruno's talk. And I was thinking, yeah, you could put, the devices they're coming out with now, you could put that right on the plane, right? You could do the inference right on the edge. Plane lands, update the model, put it back up in the air again. You're inferencing in real time up on the edge, and then all you're transmitting is the output of the model, not the whole image. I recommend you try several and compare. I'm going to be doing that as well. I think the next one I'm probably going to try is Privthy. There's been some new advances in that one, and they're doing some really interesting things, and their data set aligns closely with the type of data I'm using. There's a growing number of platforms creating data. So this came up before also in Mikkel's talk when he was talking about carbon dioxide emission. Methane Sat was just launched. I think that was put up by the Environmental Defense Fund. There's other sensing platforms. I think Planet has come out with their Tanager series, which are hyperspectral cameras. So not 6 bands, not 8 bands, but I think it's something like 100 bands, 120 bands, right? So I can't wait. I did some hyperspectral data in my PhD research. It's amazing stuff, and it's really fun to work with, and the things you can pick out. So I can't wait for the broad scale availability of hyperspectral data and the models to go with it. But somebody else, please build the foundation model for that first, so I can just consume the foundation model. Data quality is not trivial. So like if I'm thinking about my problem, besides the 110 classes, which is a big problem, most of this came down to data quality problems. And I think it would have been hard for me to see those without being able to scroll through it in 51 and doing that quick overlay and matching and stuff. But you cannot ignore your data quality. Don't get so excited about the model you're choosing and how much you tune it and all that other stuff. Like you saw the model start to plateau as to how much it was learning on those curves, as those learning curves. And I think it's plateauing at such a low number because my data was really bad, right? And there was a lot, and I was asking a lot of it. So you're really going to have to double down on making sure you've got good quality data. And as Bruno talked about, and I think Nicole talked about too, data is the availability, the amount of data is not the problem anymore. There's multiple satellite platforms out there. There's new satellite companies coming out. There's air photos being flown. There's all sorts of imagery coming out all the time. Drones, the whole thing. The real issue that we're getting to now is not the quantity of the data, but the quality of the data and making that large quantity into actual good quality so that we can drive the models in a good direction, right? And I think remote sensing brings unique challenges. So this is you do need to understand some stuff about remote sensing that's not the same as like the rest of the computer vision world. And I look forward to those challenges. I kind of like them. And I can't wait to use multimodal. I think there is a multimodal uh, SAR camera-based multimodal model right now. That's what I mean by multimodal, right? Like it's taking, or maybe it's LiDAR. Anyway, one of those two, and I can't wait to try it out. And especially since I work now at 51, because 51 can handle point clouds and it can handle imagery data. And so I'm dying to try to get that in. All right. So follow up for 51. This is just Jimmy's going to send most of this stuff, right? So you can get that later. I want to give it one last thing. Special thanks to Sumya Ranjan at Development Seed for going above and beyond. If you look in the repos, he's the one who did a lot of the work for the clay models, and was invaluable in helping me understand what was going on. So I really want to give him a special thank out.